Right. So when we say we are doing the study of straight line motion here in kinematics, we're basically following some assumptions. Okay. Now, before we get into the depth of how can we undergo the study of kinematics also, there are certain prerequisites that we need to know. Okay. So our system basically deals with SI units. Okay. And they are 7 fundamental units in nature. Okay. So there are many SI units, but fundamentally there are only 7. So what does that mean? So there are these 7 units that we're going to be using and deriving all other units. So Newton is the SI unit of force, but it's not the SI fundamental unit of force. Okay. So to understand this further, let's first prepare a list of those quantities which are fundamental in nature, like mass, length, time, electric current. Okay. The fifth one is temperature. The sixth one is amount of substance. Okay. And the seventh one is said to be luminous intensity. Okay. So mass is measured in various units, but fundamental unit of mass is said to be kilogram. Length is measured in various units, but the fundamental is said to be meter. Likewise, time is measured in seconds, but the fundamental is also seconds, though we measure it in hours and minutes. Electric current is measured in ampere, which is capital A. Temperature is measured in degrees Celsius, Kelvin, Fahrenheit. Okay, but the SI unit is Kelvin. Amount of substance is something to deal with quantity of the matter that we add into any chemical. So it's moles. Luminous intensity that deals with light is candela, small c, small d, CD. So these are some 7 fundamental units on the basis of which the entire other unit system is derived. So when we say derived, so we are talking here about the derived units. Okay. So try understanding this. Okay. This is very, very critical. So when we say force, okay, the SI unit of force is called Newton. Okay. But it is still not the SI base unit. Okay. So what is the SI base unit? We need to understand this. Now, force is calculated by the formula mass into acceleration. Now, the unit of mass is kilograms and acceleration is meters per second square. And if you see from the list of these 7 fundamental units, meter, kilogram, and second, they're all fundamental. So we have obtained the unit of force in the SI base units or fundamental units as well. So we can therefore say 1 Newton is equivalent to 1 kg meter per second square. Okay. So in our earlier curriculum, such kind of questions were explicitly assessed as part of paper 1. From here onwards, they are not assessing you on this particular section directly. So likewise, if you take the concept of energy, okay, so energy can be kinetic, it could be chemical, it could be elastic, it could be potential. So multiple forms of it, but energy is still having the SI unit as joules, which is capital J. Okay. We need to figure out what will be its SI base unit. Okay. So for that, we can take any one formula. So let's say we will take half into mass into speed square. Okay. So half doesn't have a unit, but mass is measured in kilograms and speed is measured in meters per second, the whole square. So this will become kg meter square per second square, which is same as kg meter square s raised to minus 2. So it is valid to state the fact that 1 joule is same as that of 1 kg meter square s raised to minus 2. So what do we understand from the above 2 examples is that we can express Newton and joules in the fundamental form, or you can rather say Newton and joules came into existence because of the fundamental forms and the combination of it. Okay. Now, why are they called fundamental or why are they called system international, which is SI? Okay. Now we needed a global set of units, a language which is common to science and the scientists around the world. So they had to have some 7 units which were frozen and decided can be some common terms that can be followed globally. So now if in a country the mass is measured in grams, okay, and if that comes to me, I as a country might not understand what data am I really getting, because I understand kilogram is a standardized unit and I should be therefore sharing the data according to those units only. Though nowadays this is just not a limitation, because all unit conversions are nowadays available on calculators or with conversion factors. Okay, so this is no more a problem, but yes, this is how the concept really begins with. So like these, there are going to be many quantities in physics that can be expressed in the fundamental form. And this is a journey that you will keep learning as we do more and more examples. Okay. Then because we're going to be dealing with measurements, okay, we have a certain way of writing down the numbers. Okay. So in the measurements, there are some numbers that we're going to be getting through to calculations or solving. And that number is basically finally bottoming down to a concept called as significant figures. Okay. So there are some rules to count the significant figures in a concept. So the first rule is said to be that all non-zero digit or non-zero digits are counted as significant. Okay. Example, 11 is 2SF, 12 is 2SF, 123 is 3SF. Okay, simple one. All non-zero digits are counted as significant. Then all zeros, or we can say sandwiched zeros, between two non-zero digits, are significant. Example 101. This zero is sandwiched between the two ones, so it's counted as significant. 10101. Both the zeros are sandwiched between two ones. It is called 5 significant figures. 12304. 0 is sandwiched between 3 and 4, so it will be counted as significant. Okay, so as long as the 0 is sandwiched between two non-zero digits, we say it is a significant digit. So the third one, all zeros to the left, all zeros to the left are not significant. Okay, so example 0.01, this is 1 SF. This is all to the left, so it's not significant. Okay, 0.1, this will still be 1 SF because this is a 0 to the left. Okay, the fourth one, all zeros to the right, are not significant in a number without a decimal point. Okay, so example 10, this is 1 SF. 123.0, 3 SF. 3000, this is 1 SF. Okay, these are all zeros to the right. Neither they are sandwiched and neither there is a decimal point, so they're not counted. And the fifth one, all zeros to the right, are significant if the number has a decimal point. If the number has a decimal point So all zeros to the right are significant if the number has a decimal point and the zeros are after a non-zero digit. Okay. So let's take an example. 1.00. This is counted as 3SF. Both the zeros are to the right. There is a decimal point and the zeros are after a non-zero digit. So 101.0. We have a sandwich zero as well as we have a zero to the right after a non-zero digit, and it has a decimal point as well. So it is 4SF. 0.100. This is zero to the left, not significant. But this is a decimal point number, and there are zeros to the right, followed by a non-zero digit. So this will be counted as 3 significant figures. Do you guys have any questions so far?
No, sir. No, sir.
Okay. If that's the case, I have a set of questions to ask you. So what we'll do is we will go on a rotation basis, okay, and we can have any one of you start, and then we will have around 10 questions. You guys can just answer it in order, and we will take it up here. Okay, so the questions are right here. So maybe we can start with Hemal. You.
The first one is 2 significant figures.
First one is 2 significant figures. Okay.
Yeah, so and then after that it's 4 SF.
Okay. Shriyo.
2 SF.
Okay. The next
Yes,
one,
so
guys.
one
Huh?
significant figure.
Okay.
5 SF.
5 SF.
4 SF. So, 5 SF.
5 SF. This is 0 to the right in a decimal number followed by non-zero digit. There should be 6 SF, 4 SF, 5 SF, and 3 SF. Okay. Clear till here?
Yes, sir.
Yes, sir.
Okay, great. So likewise, when we are dealing with these kind of numbers where there are significant figures involved, and now eventually everything bottoms down to calculation because we're doing addition, subtraction, and so on. Okay. So there are certain rules for rounding off in terms of addition, subtraction as well. Okay. But the rule for rounding off is having a special case. Okay. So this rule that we're discussing is rules for rounding off. Okay. So first I'll start with some basic examples. 8.32. How many SF is this?
So it's 3.
3 SF. I want you to convert this into a number of 2 SF. So what we do is we look at the first 2 significant digits and we then look at the last digit. Since this number is lesser than 5, the answer therefore becomes 8.3 because no rounding off, it's less than 5. But if I had the same number as 8.36 from 3 SF, if I wanted to be converted to 2 SF, then this would have become 8.4 because then 6 would have increased the value of 3 by 1 because it's greater than 5. Now the challenge comes, what if the last digit is 5? Then how do we do it? Meaning, if I had an example of 8.25 and if I have an example of 8.35. So this is even number, okay? So this will remain as 8.2 only. But since the preceding digit is odd here, the convention says this will increase by 1. So this will become 8.4 in 2SF. So there's a specific rule here that if the rounding of digit, if the rounding of digit is 5, okay, followed by the rounding of digit is 5 followed by zeros, okay. So the rounding of digit is 5 followed by zeros. Then the preceding digit, increases by 1 if the digit is, or rather we should just say if this digit is an odd number. Okay, this was a standardized rule. Again, we deal with a lot of situations where generally these rules don't come into existence. Okay, but as part of factual knowledge, we should just be aware of it. Okay, now when we do operations like addition, subtraction, multiplication, and division, then how should you be using the rules for rounding off? Since we will be dealing with lots of cases only for multiplication and division, I'm just sticking around only to that rule. Okay, so rules for multiplication and division. The final answer must have the same number of SF as that of the lowest SF from the given data. So in a question, you would be given data with different SF. You have to round it off always to the lowest SF. So let's take an example. 2.3. This is 2 SF. And I want to multiply this with 4. So the answer for this will come out to be as 9.2. This is then 2 SF again. But the lowest SF here is 1 SF. So this has to be rounded off to 1 SF. 9.2 will approximately do just 9. Okay, so we look at the data, whichever is the given lowest significant digit or significant figure data, we use that for rounding off. Okay,
Yes, sir.
yeah, okay.
Yeah.
So 2.3 into 4, which is 9.2, which is approximately equal to 9. Okay, so this is the rules for multiplication and division. And that's how we're going to be following it in the same way. So let's say if you had a number of 49 divided by, let's say 49.0 divided by 7.0. So this is 3 SF and this is 2 SF. And the answer we know 49 7 is 7. But because the lowest SF is 2, we have to write this as 7.0 in 2 SF. Okay. Powers of 10 are never counted in significant figures. Are we clear till here?
Yes, sir.
Yes.
Okay, great. So moving forward from here, we will be discussing the concepts of kinematics now. So when we discuss with kinematics, some of the basic parameters that come into discussion is distance and displacement. I'm going to be keeping this concept very, very small because this is something that we all should be aware of as part of our prior knowledge also. So distance is basically measured in meters. Displacement is also measured in meters. Distance is a scalar quantity. Displacement is a direction dependent quantity, so it is called as vector. Okay, distance is the actual path length. Okay, in simple terms, displacement is a straight line path length from the starting point to the ending point. Okay, so these are some of the factors that we know that displacement is basically very, very direction dependent. Distance is basically not dependent on the direction. Since these are all prior knowledge fundamentally, okay, we really don't need to spend time on this. What is more important here to understand is motion graphs. Okay, so we're going to take 4 situations of distance time graph and we're going to evaluate all the 4 situations. If we can crack it for distance time graph, we will be able to crack it for the displacement time as well. Okay, so let's say on the y-axis here we have is distance on the y-axis, time on the x-axis. So the graph is basically something that doesn't change with respect to time. So with respect to time, the distance does not change. So we say that the object is at rest. Okay, the distance did not change. Likewise, if the distance with respect to time changes uniformly, like equal distances in equal time intervals, okay, We have a graph which is a straight line, where if I calculate the slope of the graph, it's going to be distance 2 minus distance 1 over time 2 minus time 1, because this is going to be distance 2, this is going to be distance 1, this is going to be time 1, this is going to be time 2. And distance over time is basically equal to speed. So we get to learn that the gradient of a distance versus time graph, gradient of a distance versus time graph is equal to the speed of the object. Okay, so gradient of a distance versus time graph is equal to the speed of the object. So that's one when the object is at rest, one we have the constant speed. But now it is not necessary that the speed might always change at a constant, or the distance will always change at a constant rate. So let's say if you are speeding up or slowing down, we have a different situation here. So with respect to time and distance, okay, we have a situation where the graph is basically somewhat like this. Okay, so this is basically said to be the increasing speed, because the distance is continuously increasing as the time progresses. And likewise, if I start from here and eventually I start slowing down, this is basically said to be decreasing speed, because I'm eventually slowing down. So increasing speed is also known as that we are accelerating, and likewise decreasing speed is also known as that we are decelerating. Okay, so based on this graph situation, okay, tell me if I had this graph here for displacement versus time, then what would be the changes in the four graph terminologies? Anyone? Let's start from with you. That if the first graph was, instead of distance, if it was written displacement.
Yeah, sir. So it'll still stay the same, right? Because there is no displacement.
The
So
object
the
is still at
object is
rest, you mean to say.
Yeah. So it'll stay the same.
So object is at rest basically.
Yeah.
Okay. Shriyam, what about the second case? If the graph was, instead of distance time, it was displacement versus time, then what would the slope become equal to?
Velocity.
Okay. And Hemal, can you tell me if this graph was displacement versus time graph, then what would be the change in the terminology?
I'm not really sure.
So as we see here, that speed is related to distance, right? Correct? Speed is distance upon time. Likewise, velocity is displacement upon time, right? So if this was a displacement time graph, we would have said this is increasing velocity and decreasing velocity. Are we clear?
So yeah,
What, sir? I couldn't hear you.
If instead of distance we had displacement, we would have said these are decreasing velocity and increasing velocity, because displacement and velocity are relatable.
Yes, sir. Got it.
Okay. So now, how do we define acceleration? It is defined as the rate of change in velocity with respect to time. The rate of change in velocity with respect to time. So acceleration is v minus u over t, where v stands for final velocity, u stands for initial velocity, t stands for time, and a stands for acceleration. Okay, so this is the definition of acceleration. Now, as we see from here, that if I rearrange this, this can also be written as acceleration into time is v minus u, which means acceleration into time is called change in velocity. So whenever we have acceleration and time multiplied, we'll call it as change in velocity. And if you have change in velocity over time, we can call it as acceleration. So the essence over here is this, that if I take a situation where my graph is, there's a lot of derivation coming up. If my graph is, let's say, with respect to time, a velocity versus time graph, such that the shape of the graph is somewhat like this. So now this is with respect to time t. We have the initial velocity u, and likewise we have the final velocity v after time t. Okay. Now if I try to take the intercept of this graph, okay, that is basically equal to the initial velocity value, which is equal to u. If I take the slope of the graph, it's going to be v minus u over t minus 0. So that is same as v minus u over t, which is change in velocity upon time, which is acceleration. So what we can write here, v minus u is equal to at, which implies v is equal to u plus at. This is your first equation. Any doubts till here?
No.
Okay. Now comes the next part, which is said to be area under the graph. So area under the graph is this one. Here. There are two ways we can look at it. Either we look at it as a trapezium, or we can look at it as a triangle and a rectangle. So we will start first with the area of trapezium. So if you see area of trapezium, the formula is half into sum of parallel sides. So this is u and this is v. So it is half into v plus u, sum of parallel sides, into the height, which is same as that of t. So half into u plus v times t. Now, whenever we are multiplying velocity and time together, that results into displacement, because velocity is always equal to displacement over time. So if you do velocity into time, that will become equal to displacement. So S is the symbol that we use for displacement. The equation we have is S is equal to v plus u the whole over 2 times t, where S is equal to the displacement of the object. Okay. So this is your second equation, which you will find it in the formula booklet. Okay. But we can also say area under the graph is equal to, considering the fact that there is a rectangle, so area of rectangle plus area of triangle, which is a right angled triangle. Because if you see over here, this is forming a right angle triangle, whereas this one is forming a rectangle here. So this is t, so this will also be t. If this is u and the full length is v, this length will become v minus u. Okay. Are we clear till here?
Yes, sir.
Yes, sir.
Area of rectangle will be length into breadth, so it is t into u, plus area of triangle is half into base, which is v minus u, times the height, which is t. Oh, sorry, the base is v minus, height is v minus u, the base is time. So because it's again multiplying velocity into time, it has to be displacement. So S is equal to u into t plus half into v minus u over t. Now from this equation, as you see, v minus u over can be written as a into t. So therefore, we can write S is equal to ut plus half at into t. So S is equal to ut plus half at squared. That's your third equation. See, if you look at the speciality about these three equations, in the first equation, the value of S is missing. We do not have any information about the displacement, so we are able to use it. In the second equation, the value of acceleration is missing. So even without acceleration, we are still able to calculate a value. And with the third equation, you see the final velocity is missing, which means without knowing the final velocity, we are still able to calculate a value. So these are the specialities about the three equations to identify which one to use when. And therefore, it is essential to write down the data very, very carefully. Okay. We have the last equation, which is basically a combined equation. Okay. Now, we know that from v equal to u plus at, we can write this as v minus u the whole upon a is equal to time. And okay, s is equal to v plus u by 2 times t. We can write this as s is equal to v plus u by 2 into v minus u upon a. Because in this equation, if you make t the subject, you will get v minus u over a. So we substituted that here. So s is equal to, as you see, a plus b, a minus b, which means it is a square minus b square over 2a. Rearranging it will give you the equation as v square is equal to u square plus 2as. And this equation, you see the time factor is missing. But all the four equations have something common, that is initial velocity. That isn't changing. Okay. So we need to use these four equations, and these four equations are basically called to be as SU-WAT equations. Okay, a very, very important fundamental topic to understand the projectile motion concept. So it's called SU-WAT because S stands for displacement, U stands for initial velocity, V stands for final velocity, A stands for acceleration, and T stands for time. That's why it's called SU-WAT equations. They also have a name which is known as equations of motion. Okay. There are certain conditions to use these equations. Number one is that air resistance is negligible. We aren't taking air resistance into account, okay, because that's what is considered, that while you're doing this, air resistance should be negligible and the motion must be a straight line motion. Okay, clear till here? Any questions?
No, sir.
Okay, so have your notebooks ready, pen ready, calculator ready, and we're going to apply this into some set of questions, some simple questions to do. Okay, to just get familiar with the application perspective. Okay, so I'll just take this and I'll put it here. Okay, so add equations. Sheet. So what I'll do is I'll start with first explaining you how you should be writing it. Okay, so that your approach becomes easier. So whatever question we have, we just need to write SUVAT for the given questions. Okay. So a car slows down from 28 meters per second to rest. It means it was initially traveling at 20 meters per second and now it is coming to the state of rest. And after traveling a distance of 88 meters, what was its oh wait, I just wrote this wrong. I think this had to be written here. This was 0. So what will be the acceleration? Now we have a list of 4 equations, out of which independent of time is just one, v square equal to u square plus 2as, right? And we have to find acceleration. So 0 square is equal to 28 square plus 2 into 88 into s. Make sense? Does that make sense?
Yes, sir.
Yeah.
Yeah, it's not making sense, guys. You need to be 101% attentive. I have the value of s as 88. I have to find out acceleration. So this has to be not written as 28 into s. It had to be 2 into a into 88. मैं वहां पे 88 into s लिख रहा हूँ. a into 88 नहीं, हमें acceleration ढूंढना है. So this had to be written as 2 into a into 88, not 2 into 88 into s. S is already known to us. Okay. Now we clearly know that acceleration will come negative because it's slowing down. So from here we can rewrite this equation as 28 square is equal to minus 172a. Okay. So acceleration will therefore become negative of 28 the whole squared over 172. And from here you will get a negative value, and that many meters per second square is the acceleration over here. Are we clear?
Yes.
Yes, sir.
So what I'm doing is I'm listing down the four equations here. So one is V equal to U plus 80. S is equal to UT plus half 80 square. V square is equal to U square plus 2AS. And S is equal to V plus U by 2 times T. These four equations are there. Use these four equations and try question number 2, 3, 4, 5. Come on, get started.